Welcome to AP Calculus, Chapter 5, Section 2, Day 2. We're talking about antiderivatives, and we just started kind of breaching into that on the Day 1. And antiderivative is exactly what you would think it is. It's something that undoes or turns a derivative back into maybe its base function, what it was before we took the derivative. So, for instance, we know that the derivative of 4x squared is 8x. Therefore, the antiderivative, and this is my own notation right now. We'll be talking about different notations for finding antiderivatives or doing antidifferentiation. The antiderivative of 8x should be something along the lines of 4x squared. And I notice, well, 4x squared, the derivative of that gives me 8x, but so would, here's my little thought bubble, what if I had 4x squared plus 6? The derivative of 4x squared plus 6 is also 8x. So our antiderivative, it says, a function f of x is an antiderivative of a function f of x if f prime of x equals f of x for all x in the domain. The process of finding an antiderivative is antidifferentiation. We also had another rule that we got to that talked about there's always a possibility of a constant. In this case, I could add any constant, nothing with x in it, but any constant. I could add pi onto this, I could add e onto this, I could add ln of 7 of it onto this, or I could add any constant. So our when we do antidifferentiation, we may get enough information to find out what the constant is, and you'll see problems like that in this example. But if we're just flat finding antiderivatives, we have to go ahead and put this little plus c and make a note, at least in our heads, that that is any constant value can go there. Okay, find all possible functions f. When they tell me all possible, that means it's not just 4x squared in this case. It will be 4x squared plus c. There's an infinite number of functions that have a derivative of 8x. So we're going to get rules for this, and we may be able to even devise them as we're going through some examples. But what we're going to do with this is we're just going to try to think our way through this. If I have a derivative that is now x to the first power, it must have started out as x to the second, because that's what derivatives do. They reduce the exponents by 1 if x is the base. But the derivative of x to the second isn't x, it's 2x. So I would need something to cancel that 2 to get me to x. So if I did this, maybe that is what plain old f of x, or our position equation, would be. Let's take a look. Take the derivative. I get 2x divided by 2. That is x. If I want all possible, plus c. Now again, maybe at this time we'd want to just start exploring rules for, if I have x to the 7th, what am I doing? If I have x to the 12th, what am I doing? Maybe even x to the negative 4th, I can have a rule for that. We can start playing around and trying to be scientists and come up with rules for this. But that's not what I'm going to do right now. I'm just going to fight through it each step of the way. Okay, so B. They tell me the derivative is this. The derivative is a second degree polynomial. So the original function must be some third degree polynomial. And a quick look here. Once I know it's a third degree on x, I just check what's the derivative. The derivative of this would be 3x squared. Oh, I'm already good. I'm already in good shape here. So I got this term knocked out. And maybe I would have a minus. If the rest of this is first degree, then I need second degree, so I'm going to leave a little room in case I need to do some adjusting. But I must have an x to the second, and I take a look, well, what if I just use this derivative? X to the second derivative is 2x. Oh, this is a pretty nice problem. And the derivative of what gives us plain old 1? Well, the derivative of 1x gives us plain old 1. So that is a function whose derivative is this. We're just working backwards now. But we're supposed to find all possible functions. And I know that the graph of x cubed minus x squared plus x looks just like the graph of x cubed minus x squared plus x plus 11, except the second graph would be 11 steps higher. I still need to include that plus c. C could be any constant. Okay, part C. When do I get e to the x as a derivative? I get e to the x as a derivative when I take the derivative of e to the x. The derivative of e to the x is e to the x, but so is the derivative of e to the x minus 7, or plus some constant. Okay, there's going to be some challenging antiderivatives, but they're really trying to get you to fight through these without any rules at this time. We'll have lots, believe me, you will see lots of rules.
Jack Raggerty, please report to the visitor's desk. Jack Raggerty, please report to the visitor's desk.
Excuse that brief interruption. But you're going to get plenty of rules, believe me, on how we're going to handle more challenging antiderivatives, but we ought to be able to formulate some plans through here. And again, I think it would probably be a really good idea now just to try to come up with your own rule on, for instance, if we had x to the 9th, what would it be? Okay. Now, look at the directions, it seems similar, find the function. And I said earlier, sometimes we have enough information to figure out what c is. This says, well, we still got this whole derivative given, and now we're supposed to go back to the plain old function, find the function with the given derivative. So I'm going to think of f prime of x right now being negative 1 x to the negative second. What kind of function, forget about the negative 1, would, after I take the derivative, would end up with a negative 2 exponent on x? That would have to be a negative 1. Like if I take the derivative of this, I end up with a negative 2 up here. But good news is, I also end up with, if I take the derivative of this, a negative 1 out in front of my x to the negative second. So this is 1 on x. And now, that is some of the functions, but again, we can still have plus c for that. So at this point, I've got f of x is 1 on x plus some constant. However, I've got a point that lies on this function. It says find the function with the given derivative. We're finding the function whose graph passes through this point. Therefore, when y is 1, x is 2, and I learned that c equals 1/2. So if c is 1/2, f of x must be 1 on x plus 1/2, and maybe we could leave it that way, but I wouldn't be surprised if back of the book got common denominators. Need a factor of x, a factor of 2. This had to be multiplied by 2 on 2. This had to be multiplied by x on x. Okay, it'd be a really good time to pause and try B. Our first thought, if you pause, great. If not, just follow along here. Our first thought might be maybe we want to treat this as f prime of x is x plus 2 to the negative first. Well, if we treat that as x plus 2 to the negative first, what kind of exponent would we need to get to negative 1, taking the derivative? We'd need 0, and then our worlds kind of collide at that point. So, can't have an exponent of 0, but how else can we get a 1 on? If I was to take the derivative of ln of x plus 2, that would be 1 on x plus 2, and I don't even have to make any adjustment here. Like, I don't have to apply for put a negative. If this was a 3, it would be a different story. I might have to put a 3 here, a 3 here, somewhere else. But the derivative of ln x plus 2 is just 1 on x plus 2. Okay, and then they tell us that, and of course this would be plus c, because the derivative of this is still 1 on x plus 2 plus 0. But then they tell us we've got an ordered pair. Y is 3 when x is negative 1, or 3 is ln 1 plus c. That's convenient. this is the exponent that turns e into 1. What is the exponent that turns e into 1? 0. C is 3, so I end up with f of x is ln x plus 2 plus, was c, but now see, here's what we had. We had the shape of a function right here. I know ln x plus 2 looks something like this. We just had to force that to go through the point -1, 3. And then, as it turns out, this forces us through the point -1, 3. Okay, not too bad. Believe me, anti-differentiation is going to get more challenging than that, but again, you're going to have some rules along the way. Here are some very, very worthy problems for AP Calc test where you're given information and asked to draw a sketch of it, and the opposite's true as well. Sketch a graph of the differentiable function y equals f of x that has these properties, and this is taking us back away from antiderivatives. We have to have a local minimum at 1, 1, and we have to have a local maximum at 3, 3. And there could be a lot of ways that we could do this. So I'm just going to call this one's I. We got 3 separate problems here. We have to have a local minimum at 1, 1, and we have to have a local. We got to make sure they're just locals. A local maximum at 3, 3. So this is a local maximum, but not my overall maximum. But if it's a maximum, I could have a cusp, but likely I just have a nice smooth where the slope is 0, and this has to have slope of 0 here. And then to make those be local, I have to make sure somewhere I get lower than this point, somewhere I get higher than this point. I mean, I guess you could still call them local minimums. An absolute minimum is a local minimum, but we're going to go ahead and do it very, very literal here. So this could just come down here, touch this, and maybe go up forever. If this goes down forever, that would meet our needs. I mean, I could still have this thing come out of here, wiggle around, wiggle around, wiggle around, go down forever, but that would be just a little bit of overkill. So in its simplest form, this might be the best way to get the job done. Stole some of my space there. Local minimum at 1, 1, which to me is making me think, unless there's some reason to make it a cusp, we're looking like this. And at 3, 3, we need another local minimum up here, which means I'm going to have to get above here and come back down. Sketch a graph of a differential. If it's differentiable, it's continuous and it's smooth, so there goes the cusp idea. So I'm going to have to come up above there, come back down. Now, this would be a local minimum. This would be an absolute minimum. But if I wanted to make this just be a local only, I could always, there's nothing saying here I couldn't take this back down. But again, if you let it keep going up, it's still a local minimum. That's a local minimum. Okay, and I'll squeeze one in here. I have a local maximum at both. So if this is a local maximum, it must look something like this if it's differentiable. And if this is a local maximum, it must look something like this. So, and if it's differentiable, I can't take a corner point and go up there. I've got to stay smooth, but I've got to get up there at some point. And again, we can get into the whole, are we going to be literal and make it be only a local maximum? And we could send this back up. But it is definitely, it meets this, our literal requirement here. This is definitely still a local maximum, even though it's the absolute. Okay, and B. My first look at this one, I thought that I was trying to do 4 separate graphs, but it's not. This is all one graph, and so we may have to have some planning here. This tells me my slope at -1 is equal to my slope at 1, and the slopes there are 0. Now, it doesn't tell me where I'm at, and if you notice, we're really only dealing with slopes the whole time, so I don't really care if I'm up at 100 or down at -20. So I'm going to build a decent-sized graph here, and I'm going to say my slope at -1, my slope at 1 are going to be 0. I'm going to put those on there, but I better read ahead a little bit. my slope of x from -1 to 1 is going to be positive. And this is still falls under these same, it's differentiable, so smooth and continuous. So I have to be going up from -1 to 1. I'm going to give this a shot. Maybe I'll have to come back and cross that out and start again. But this satisfies if my slope is 0 here and my slope is 0 here instantaneously. This is set to satisfy the first two conditions. Slopes are 0, and for all my x values between -1 and 1, they're positive. I know they're not positive right here, but between the two, they're going to be positive. I can't wiggle back down. Then it says my slope to the left of 0, or excuse me, that's not right. It says my slope is less than 0 to the left of -1. So to the left of -1, I have to be coming down to that. So this has to head back up that way. And we have to be increasing in here. Let's see. My slope is bigger than 0. I have a positive slope to the right of 1. I have to be heading up eventually. So I come out of here flat, come down to there flat, and I've got to go up forever. Now, on an AP test, they may give you that information and then ask questions about it. They may say, is there an absolute minimum? So to test whether you drew it right. Is there a relative minimum that is not an absolute minimum? Is there an absolute maximum? What's the end model behavior? There's a lot of questions we could ask off of giving this. Okay, so other than, we're going to have to do some thinking through here. Pretty straightforward for day 2 on our Chapter 5, Section 2. These are problems that will add to that assignment. There will be a video available for those. The 51 through 56, just going to warn you right now, the 51 through 56 start multiple choice, and I think those are better handled through discussion in class than they are with me just revealing the answer on the video. Those are problems that you should go to and be thinking on your own. Maybe they all are, but particularly those multiple choice ones. Okay, well, thanks for tuning in, and see you soon.